Behind every fire alarm you've ever seen, every sprinkler head, and every one of those glowing exit signs, there's this deep, unseen science at work. It's a whole world of complex calculations and split-second decisions that really determine who gets out safely.
So it makes you wonder, right? How does one tiny single spark manage to escalate into a full-blown citywide emergency? That's the big question we're going to dig into.
And the answer, well, it goes way beyond just things burn. It's this fascinating chain reaction of physics, some really clever engineering, and of course, the total wild card, human behavior. So let's follow that thread, starting from the microscopic and taking it all the way to the massive.
Okay, let's start at the very beginning, with the anatomy of a fire itself, from a single spark to a full-on flame. This brings us to a really cool concept called flammability limits. See, a fire isn't just some chaotic random event. It can actually only exist inside a surprisingly narrow set of physical conditions. You can almost think of it like it's walking a tightrope. And this quote from the research really spells it out. For a flame to keep going, the time it takes for the chemical reaction to happen has to be almost perfectly balanced with the time it takes for heat to escape. If it cools down too fast, the flame just dies. And if the reaction is too slow, well, it never even gets started. It's truly a delicate dance of energy.
So, we've seen how a flame can exist out in the open. But what happens when we put that flame inside a room? This right here is where things get really, really dangerous.
Yeah, once a fire gets trapped in a room, it's not just burning fuel anymore. It starts to create this powerful feedback loop. The heat has nowhere to go, so it radiates down from this growing layer of smoke at the ceiling, basically preheating everything else in the room and pushing it all closer and closer to a critical turning point.
And that turning point has a name, flashover. It happens in these very distinct stages, and it is terrifyingly fast. First, you get ignition, a small fire. Then, a plume of hot gas creates a superheated layer right at the ceiling. That layer then acts like a giant broiler oven, radiating intense heat down on everything. And then, flashover. The entire room just erupts in flame as everything hits its ignition point all at once.
Just look at this chart. It shows you exactly how fast this happens. In just a couple of minutes, a room can go from being manageable to completely unsurvivable. And that tiny, tiny window of time is precisely what fire safety engineering is designed to fight against.
So, if that's the problem, what's the solution? Well, this brings us to the engineering response. How do we fight back?
It all boils down to this one simple but powerful equation. The entire goal of fire safety engineering is just to make sure that the time you have available to escape is greater than or equal to the time you need to escape. Every single system, every rule, it's all designed to tip the balance of this equation in your favor.
So how do engineers actually do that? Well, let's look at two common suppression systems. Water sprinklers. You know them. They're incredibly effective because they attack the fire directly. But then you have something like a halon gas system, which has a pretty critical weakness. It needs a perfectly sealed room. Just one single open door can make the whole system useless and allow the fire to spark right back up. But of course, it's not just about sprinklers and gas. Engineers use a whole multi-layered defense system. Things like high-expansion foam, portable extinguishers, fire-resistant doors that create safe compartments, and smoke control systems that keep escape routes clear. It is all about buying more time. But all that engineering, it's only half the story. The most unpredictable variable in a fire isn't the fire itself. It's us. This next part is all about the human element. Take a look at this number. One survey found that 14.2% of adults in Great Britain have a disability. So what does that mean? It means evacuation plans can't just be for the young and the able-bodied. They have to work for absolutely everyone. And that is a massive challenge for designers. To try and tackle this, scientists don't just guess. They use these incredibly complex computer models, they're called stochastic simulations, to see how crowds actually behave during an evacuation. And these simulations show, really clearly, how even tiny delays can have huge consequences. Let's actually look at the results. Okay, in case A, the alarm goes off in just 15 seconds. The system works perfectly. And the result? Take a look at the potential victims bar. It's almost at zero. Nearly everyone gets out safe and sound.
Now let's look at case B. The only thing that's different here is the alarm is delayed by just under 2 minutes. Now look at the potential victims bar. Whoa, it has jumped up significantly. That small delay is the difference between a close call and a tragedy.
And then you have case C.
This is what happens when the detection system fails completely. The alarm is delayed by over 30 minutes, and the result is, well, it's catastrophic. This really drives it home. Early detection isn't just important, it is the single most critical factor in saving lives. Period.
All right, let's zoom out one last time. We've gone from the individual and the room all the way up to the citywide response, where planners have to prepare for chaos on a massive scale. And the key takeaway here is pretty simple. One-size-fits-all emergency plans, they often fail. As the research puts it, stereotyped emergency planning may not be sufficient or acceptable. Every single location, every event has its own unique challenges, and they all need unique solutions.
And here's a fantastic example of that principle in action. For the Expo 92 World Fair in Spain, planners had this huge problem: how to evacuate thousands of people from an island. So instead of just adding more signs, they built the evacuation plan right into the infrastructure. The main road was elevated, which let people flee underneath it through underpasses to a designated safe zone. Safety wasn't an afterthought, it was part of the fundamental design.
And a huge part of any large-scale plan is communication. This simple, memorable message, go in, stay in, tune in, was actually developed for chemical incidents. It's clear, it's actionable, and it tells the public exactly what they need to do to stay safe. It's a tool, just as important as a fire hose or a sprinkler.
So, ultimately, what all of this shows us is that fire safety is a science of calculated trade-offs. And that brings us to a final, very difficult question, one that comes directly from the research. In a museum fire, a night watchman is trapped. How many firefighters is it acceptable to put at risk to save that one person? There's no easy answer, and it's that tough ethical calculation that lies right at the very heart of emergency response.